Hello, everyone, and happy Steel Day. Welcome to this year's Steel Day webinar, this year being presented by Brian Morgan. My name is Nate Goner with AISC, and I will be your moderator for the webinar today. I would like to introduce this year's Steel Day webinar speaker, Brian Morgan. Brian Morgan is a principal at Magnuson Klemensic Associates, a consulting structural and civil engineering firm based in Seattle. He received his Bachelor of Science in Civil Engineering from Washington State University and both a Master of Science and a doctoral degree in Civil Engineering from the University of Notre Dame. As a senior member of MKA's Office and Residential Specialist groups, he has experience managing office, residential, and mixed-use projects, including towers up to 68 stories and developments with multiple structures totaling up to 8.1 million square feet. Dr. Morgan also mentors MKA's performance-based seismic design technical specialist team focused on advancing building performance and developing and improving seismic design methodologies. He often takes the lead for projects in areas of high seismicity. He is currently the project manager on Rainier Square Redevelopment in Seattle, and we are grateful that he's here today to talk about that project and its use of the revolutionary SpeedCore system. Brian, thank you very much for being here, and I'll now turn things over to you.
Thank you very much, Nate. I'd like to extend my great thank you and gratitude to AISC for this opportunity to share and discuss this topic as well with such a large and very interested audience that I can see by the number of participants here. Today we're going to be talking about SpeedCore, or the composite plate shear wall system, and its relationship and advancement and use in the Rainier Square project in Seattle. So today we're going to be talking a bit of a brief overview of SpeedCore in general, some of the beginnings of where it exists in the code and what its roots are. We're going to spend the bulk of the time really though in this real-world case study of Rainier Square, where you can see this photograph on the right of a panel of this system being tripped up and being ready to be placed in the building. And we're going to summarize at the end and talk a bit about research and code integration of where things are headed and what are the next advancements for this sort of technology to be used in building construction. So I'm first going to start very briefly with a SpeedCore overview. In terms of AISC 341, the 2016 standard, the system is known as a composite plate shear wall concrete filled. You'll see this acronym C-PSWICF. That essentially is what we would call a sandwich panel system. And we're going to go in and talk about the parts and pieces and the components of the system. In terms of ASCE 716, the system in terms of loading and R factor, it would be considered a steel and composite plate shear wall system. And in this diagram here on the bottom, what we're talking about is a system on the left of what I would call a traditional reinforced concrete shear wall comprised of rebar and formwork, and moving to the right, an alternate version of that where you don't have formwork and you're replacing that with this composite plate shear wall system that is filled with concrete. The system highlights and the project benefits, we've listed several here, and we'll talk a lot about these as the presentation goes on during the case study. But in terms of the highlights, if we look at it, we have modularity and prefabrication of the steel modules off-site, tight tolerances, ability to erect fast in the field. We eliminate rebar and formwork for the pouring of the concrete because we use the reinforcing side plates as the formwork. We get strength and stiffness and ductility out of this system to resist wind or seismic or other lateral loads. There's a single trade tolerance in terms of construction trades. We don't have differing standards of practice in terms of tolerance relative to concrete construction per ACI and AISC for steel. All of the tolerance for the erection of the tower is under one code of standard practice, which in this case is AISC. Schedule reduction. We'll talk a lot about that because as what you'll see and learn in this presentation, That was one of the main driving forces for the project moving forward, was the schedule reduction that was achieved using this system. Construction cost savings, obviously, due to schedule reduction, you can reduce your construction costs. And from the owner perspective, the sooner you can get to market, you have reduced financing costs and you can get earlier income. So we're going to jump right into the Rainier Square redevelopment project in Seattle, Washington, and talk a little bit about its history, talk about the parts and pieces, and talk about the structure. This will make the bulk of this webinar in terms of the timing. The image you see here is a cover story in ENR that was dated January 1st of 2018. It's interesting to note that the date of that was prior to any project mock-up, it was prior to any fabrication, it was prior to detailing, and it was prior to any erection on site. What that meant was this article, in consultation interviewing the developer, the owner, the engineer, the contractor, and all the parties involved in terms of the fabricator and erector, it had a lot of promise and a lot of hope, but all of that was on paper. And so what we're going to talk about today, a year and a half later, is that paper has become a reality. The project team, just for full disclosure, the client was Wright Runstead and Company here in Seattle. The architect was MBBJ, and Magnus Klemensic Associates provided structural and civil engineering consultancy services. Lease Crutcher Lewis was the GC. The Supreme Group was the fabricator, and the erection company was the erector. In terms of the people we're talking about making the decisions and the design and the implementation of the SpeedCore system, these were the big players. As a project, it's a very large project here in Seattle. It's a 1.4 million square feet project comprised of a signature 850-foot tall tower. That tower is a 58-story office building with residential on top. If you look at the image on screen here, the lower portion of the building here was the office portion, and the upper portion was the residential portion. There's about 725,000 square feet of office space, 200 apartment units. There's a side hotel that's a component of it, and there's 1,000 below-gate parking stalls. We love our parking in our cars here in Seattle, it looks like. If we look at a floor plan now, starting at the base of the building, where if we look at this unique shape of the building where we have this swooping nature of the site, or the shape of the facade, you can see that we start at the base of the building with a three-cell reinforced we started the project, with a three-cell reinforced concrete core. We've developed the project through schematic design as what I would call a traditional system of reinforced concrete core. It provides the strength and stiffness that we need to resist seismic and wind loads. And we'll ultimately talk about why the switch to SpeedCore was so profound and needed for this particular project. At 850 feet tall, if you look at the building proportions here, you'll notice that the width of the building in the page left-right here is quite short. It's about 40 feet. So relative to the height of the building, it's got a very small aspect ratio. To be able to resist adequately wind, seismic loads, and have good occupant comfort, we needed to increase the stance of that building. What you'll notice here is these very large columns that are flanking the outboard sides of that direction. These are what we call the Outrigger columns. And you'll see here in some subsequent slides, we use buckling restraint brace Outrigger trusses to engage those columns to get ourselves a bigger stance in this building direction in order to have a good aspect ratio to resist these seismic and wind forces. In the other direction, we're about 90 feet, which is adequate for the length of the building given the height of this building. The color coding diagram here you'll see is just how the elevator stacking works. What you have here is a low-rise office lift, you have a high-rise office lift, you have a fire service access lifts that serve full height, and then at the low floors you have two residential shuttles. As the building facade continues to move inboard on the east side of the building, which is page top here, you'll notice that the three-cell core drops to a two-cell core. The low-rise office elevators dropped off, and the high-rise and the residential shuttles continued. Once we get above the Outrigger level, you'll notice that it becomes a very traditional square footage floor plate for residential, and it's a single-cell core. So along the height of the building, we have about a third of the building height is a three-cell core tapering to a two-cell core tapering to a one-cell core. And as I mentioned, this was the lateral system. Given the height of the building and the aspect ratio, around the 2/3 point of the building here, we engaged a outrigger and belt truss system to engage those outriggers to give us adequate strength and stiffness of the core, essentially supplementing or providing what we'd call like a ski poles. If you're a skier, you get your ski poles to provide better balance. And we proceeded through schematic design with a traditional reinforced concrete system. We've been doing, for the past 20 years, that type of system has been kind of the flavor of the week in terms of commercial office buildings with a concrete core and a steel floor framing around it. And what that looks like in construction, at least in high seismic zones, where we have a tremendous amount of reinforcing that's required to be put in the core, what we find is that this picture here shows an example of a typical construction sequence. This happens to be from a project here in Seattle. And what you see is that the concrete core is let out well in advance of the trailing steel framing operation. The reason for that is that it takes nominally, very rough order of magnitude, about twice as long per floor to build that reinforced concrete core than it does to build that steel floor framing there. And what we find is that the concrete core is the critical path of the project. All the elevatoring goes through that core. And so we started to scratch our head and say, how do we begin to improve the speed of construction of that core? How do we get it off the critical path, or how do we, and if you can get it off the critical path, every day saved is a day delivery of the project sooner to the client. So here's an example of a 40-story building. The core was jumped up about 20 floors, and then the steel erector mobilized and met at the roof. What we find on Rainier Square was we have this very intricate and detailed and steel-heavy structure that's occurring at this two-thirds point. This two-thirds point is strategic in its location. It's the delineation between the office floors below and the residential floors above. And this is an ideal location to put in some that additional structure to get the building stance that we need to resist seismic and lateral forces. But the amount of steel here and the demands on the core in this region really drove the schedule. The contractor, when they went out for schematic design as a concrete core, you can imagine the amount of steel elements that need to traverse through this wall. The shear demands are incredibly high, and to the point where it was almost undesignable in concrete, to where this ultimately ends up becoming a nearly solid steel truss or plate inside of the wall. When the contractor went and put together their construction schedule, which sort of looked like this, they got a certain cadence of construction, and it led to a construction schedule. If you look at what their construction schedule was, they were going to jump the core out ahead, mobilize the structural steel framing, which can nominally go twice as fast, and they would meet up at this interstitial BRB level. That level, they were estimating, would take several months, many months to build two floor levels, on the order of about 3 months to construct. Once that was constructed, the concrete core would jump out ahead again, and the steel would be remobilized to meet at the roof. This is what we would consider kind of the traditional concrete core construction schedule that the contractor put together for the project based on the schematic design at the time. What we found out from that process was the owner was looking for any way to bring down costs and increase the schedule. We'll talk about numbers here shortly on terms of how long things took in that original sequence, but in the end, the project was in danger of not moving forward. We had a system that cost quite a bit of money and took a long time to build. And so we threw out the idea of utilizing a relatively new system that's in AISC, which is the composite plate shear wall concrete filled system. What you see here is a series of steel plates with cross ties attaching them. They happen to be broken up into segments, in this case, of corner columns that you can see here, which are essentially our box column elements, and panels. We have two types of panels. We either have a solid panel where there's potentially no door openings, or we have what we call a dog bone or an H panel where we do have door openings coming in out of the elevatoring or back of house spaces of a core. And what we are able to do with this is essentially prefabricate and integrate all of the requirements of the core outside of being on the field and in the shop. We're able to pre-install the cross ties. We install these panels. They come on a truck. All of the ledger angles that are required to support the deck are pre-installed. All of the shear tabs for all the incoming beams are pre-installed. All of the MEP penetrations are pre-installed. So everything comes in prefabricated and pre-coordinated. And you're able to erect this steel in sequence with the steel floor framing. And the last step of the process now is the concrete infill that you see here. And that is a trailing operation where you're pumping full the core as the core is being erected ahead of you. So you're several levels below the active erection deck, and you're filling the core roughly at the same time or just in advance of filling the composite deck floor slabs. So the concreting operation becomes a completely trailing operation. And if we go back to our elevated construction sequence that we showed previously, where we were jumping the core out ahead, in each of those situations, we're now erecting all of the steel framing, core, and floor framing in sequence, and there is no starting and stopping, and there is no delay between that core construction speed and timing versus the steel floor framing. If we talk about the parts and pieces of the system, we're going to dig into that a little bit here with the next few slides. The composite plate shear wall construction was comprised of essentially two elements. There are outer face plates or side plates of various thickness. In this case, all of the wall thicknesses were nominally a half-inch thick steel plate on each face. That comprised about 75 to 80% of the entire core. There are some zones at higher demand levels where those plates were increased to 3/4 inch. And then up at the outrigger levels, there are some zones where the BRB connections and gussets come in are on the order of 2 inch. The wall thicknesses were nominally 21 inches to 45 inches, nominally 2 feet to 4 feet thick, with the largest thicknesses down at the base of the building and tapering as we moved up the building. The cross ties are 1 inch diameter cross ties that were spaced 12 inches on center, both vertically and horizontally on all wall faces. We utilized a 10 KSI self-consolidating mix to fill it. The plates were ASTM A592. We specified a yield strength of 55 with a tolerance of 5 KSI each way because we wanted to have a good known predictability because we were doing a lot of capacity design principles. We wanted to have a very good tolerance in terms of where the yield range for the plate was. So that was a requirement for the project. If we talk specifically about the cross ties are there for multiple purposes, but their configuration is really left up, in this case, to the fabricator. We showed them options where these could be all threads with double nuts on each side. Maybe they wanted to weld one side and have a double nut on the other side. Or maybe they wanted to weld one side and have a plug weld. Or maybe they wanted to have the rods protrude through and do a fillet weld on the outside. In the end, this was contractor choice based on their fabrication means and methods, what was the most economical solution for them. In the end, from a structural engineering perspective, we only ask that the connection of those elements is able to develop the yield strength of the bar. That is a requirement per AISC. So provided we can develop the yield strength of these cross ties, the world is the oyster, is kind of the term I would say for the fabricator and how they want to proceed to move forward with this. On the case of Rainier Square, the Fabricator Supreme Group chose the option we show on the right, where the rods were not threaded. They were grade 55 rod material, and they were passed through about 3/4 of an inch and were fillet welded on each side. In the case of Rainier Square, when you space these at 12 inches on center, both vertically and horizontally, you end up with about 240,000 cross ties in the building, which means there are 480,000 welds to make. You can imagine that any sort of ability to optimize that spacing of 12 inches and or the ability to automate that welding process, every minute that you can save on that weld is an important minute saved when you're doing it 480,000 times. Now, if we look at how the panels and the core columns came together, we're going to talk a little bit about where the field splices were chosen to be. In the case of this particular project, the erector and the fabricator chose to break the panels at the corners and develop what I called earlier a box column at the corners. What that allowed them to do was erect the corner columns and get them plumb and true, and then infill with the panels in between utilizing a field splice. Now, on the vertical, you can see that they have a field splice in 4 locations at the corner, on each face coming in the corner, and then you can imagine that there's a third side horizontally that needs to be made. If we look at the chosen weld that was proposed for this project by the fabricator or the erector, this field weld was pre-qualified through testing to validate that it was a capacity weld where we were not failing the weld and we were delivering the full capacity of the plate and yielding the plate outside the weld. So this was a full depth PJP weld with a reinforcing fillet sized in order to develop the capacity of the plate. This PJP weld was chosen by or suggested by the erector mostly because of the field inspection requirements. If we call that a CJP there's really no way to get to the inside of that wall and do any sort of repair. So rather than worrying about that, we did a PJP with the reinforcing fillet. That same weld was utilized on the vertical surfaces as well, as you can see here. Again, I'll go back one more here, but again, given the size of Rainier Square, there's about 36 miles of this weld in the field to perform. So again, this was suited very well for the Seattle market where this particular erector and fabricator had the knowledge and the team to be able to pull that off. If we look at coupling beams, we extrapolated that same methodology. Coupling beams are essentially built-up box-shaped elements, tubes, that are infilled with concrete. In this case, in addition to the infill of concrete, we also put cross ties both directions again. What research, we'll talk at the end about research, would show that you probably don't need any of those cross ties through that section provided you meet certain slenderness ratios. But again, with Rainier Square, given the limited research that was available at the time, we chose to be very conservative on this approach and provide additional confinement in the coupling beam elements as well. Now, we're going to do a quick little video here, and I'm going to talk over this as we do it. On the left-hand side, this is a video we put together before we had contractor input, and we were trying to explain to the owner the potential benefits of switching to the system. So what you see on the left here is the traditional concrete core, the original drawings that we did in schematic design. This was a concrete core with concrete below-grade framing, and it switched to steel framing once we got above grade. On the right is what we proposed in our revised schematic design to move forward with, which was below-grade steel, composite plate shear wall core, the SpeedCore, and trailing operations of concrete. And when we first put this together, there was a difference of about 4.5 months, which we were extremely excited about. And to us, 4.5 months was lofty, and if we could achieve that, we were extremely excited. This video has now been updated, and what you're seeing on the right is the actual day-by-day sequence of what really occurred in the field. The building is now topped out as of about a month ago, and what you see on the right is what was actually achieved day by day. And what you see is that we are already at the Outrigger level on the version on the right, and we are barely getting out of the ground on the left. The core is jumping up, and we're nearly just about 1/3 of the way up when we're already 2/3 of the way to the top on the picture on the right. So as we're approaching August 15th of this year, which is about 6 weeks ago, we had our topping out. That is the date which you'd see over here on the right of the screen. On the left, we're speeding this up because this video is taking a long time, but we eventually want to show what the contractor had estimated the construction sequence of the traditional concrete core with the Outriggers would have been. And what we found was it was a difference of about 91 weeks versus 50 weeks. And when we originally thought this was going to be a 4.5 month savings, what we found out was the contractor had estimated that it was a 9-month savings. So incredibly thrilled with that. It was very pivotal in the decision, and ultimately the owner took the risk of doing something that really had never been done before to really try to utilize and achieve these savings. One item of note here is that this was the original estimates that were put out at the same time as that ENR cover story. When we talked about this was on paper, this was what the advertised savings was going to be. 21 months versus 12. What we really found out in real life is that the concrete or this composite plate shear wall core, the SpeedCore, topped out on exactly 10 months. And today, the concreting operation is completely finished. So this number was actually shaved down to about 11 months. So in the end, it was about a 10-month savings over the traditional system. Now, we're going to talk a little bit about the roots of the project. And so Charles Pankow Foundation, AISC, the Magnus Klemensek Associates Foundation, and Purdue University have co-collaborated and supported research that is ongoing today and that has been done in the past decade on this system. The original studies were done from 2006 to 2010, and what you see here is the original researchers at Purdue with a 5-story test specimen behind them. What you can see, this is a T-shaped specimen, and in these specimens, they were scaled about half scale, and here they chose to do the cross ties using threaded rods and nuts. We're going to talk a little bit more about the importance of the cross ties when we see a bit more pictures here. They also tested the stability of the unconcreted section. So if you think about the construction sequence that we talked about, the core is being placed in sequence with the steel floor framing on a tier-by-tier basis. And the weight of that system, lay-down decks, and the weight of the unconcreted steel needs to hang off of this unconcreted core for some number of levels. On Rainier Square, the trailing operation of the concreting was on the order of 4 to 6 levels at a time. So at any point in time, we would have as many as nominally 4 stories of construction that would be unconcreted. Those cross ties, which we can talk a little about, provide the stability in the unconcreted condition. They provide the stability during erection, and they provide the stability during shipping. Once concrete is poured in those cross ties are now going to serve essentially as your form tie that you would have in a traditional concrete system for the formwork, resisting the bulging and resisting those hydrostatic pressures from the concreting operation. And then those cross ties, once the system is composite, now it's going to act compositely, just like a shear stud does for normal composite construction. So the cross ties are incredibly important. They serve many purposes. This is a picture of some additional research at Purdue, which is ongoing today. And in this picture, we talk about different sort of configurations of cross ties, shear studs, spacings. An important note on Rainier Square, given where the research was at, and given the peer review that the very difficult peer review that obviously doing a world's first would entail, we want to ensure that the main object was achieved, which was building the building, scoring the touchdown, so to speak. Things like optimizing cross-tie spacing, optimizing the field weld, optimizing the plate thickness. In many cases, we took conservative approaches at nearly every turn in order to be very conservative, given this is the first time it had been done. Create a level of comfort with the peer reviewers in the city that we have an adequate level of conservatism in the design. What you see here is the next round of testing that's ongoing today. It's been completed, but what this is really trying to do is how can we optimize those 240,000 cross ties? Can we put them at a different spacing? Do we put them at a tighter spacing in zones where we anticipate higher ductility demands, or can we space them out in zones where we have less ductility demands, or where we assume that we're going to be elastic? What is the right spacing for wind country versus seismic country? Those are the types of questions this research is doing. Now, in terms of research for the project, I think we also did quite a bit. The contractor did quite a bit of quote-unquote research themselves in the form of mock-ups. There's 2 big components to this system, right? There's the concrete fill operation, and there is the steel plate panel production and erection. So the contractor being very concerned with making sure and ensuring good quality assurance, good quality control, to confidently be able to place concrete so that there were no voids, underwent several different rounds of mock-up testing. This particular mock-up you see here is, rather than building it out of steel and trying to disassemble it and view if you were able to achieve all the very difficult void areas or potential void areas, what they did is they built it out of plywood, and they replicated all of the worst conditions for congestion that are in the project, and tried different fill operation techniques, and they tried different mix designs. And in the end, they were able to then strip this and pour it in a certain manner. I joke a little bit about them here because when they did this mock-up, we said, well, make sure you don't look over the top of the wall, because that's the first thing they did. Because in real life, you never have the really opportunity to look down on the concrete being placed, because there is 4 floors of wall construction ahead of you. You're essentially pouring through access ports in the blind with cameras to view or visual cues or telltale holes that provide you to show you that concrete is filling up everything, vent holes, things of that nature. But this was a very important process. You can see here all of these form ties replicating the size and spacing of the cross ties. You can see this concrete placement, which was a 10 KSI self-consolidating mix, no vibration required. And at the end, they were able to strip this and feel very comfortable that they would be able to achieve a good concreting operation out in the field. Of interest, they were able to achieve quite good success in placement. They were able to place upwards of 100 yards, 120 yards an hour, given the pumping operation that they were doing. So they were able to achieve a very good pump rate to fill this wall. They also did a corner section mock-up of a typical panel construction well before we went and approved all the shop drawings and well before all of the actual fabricated materials that were going to be in the building were being done. Again, the goal here was to replicate all the different parts and pieces in the most congested areas that there would be. And really this provided a lot of information for the erector, looking for little issues in terms of fabrication, runoff tabs, backer bars, things that would hold up the operation in the field. So these are some pictures of those original test specimens, or not test specimens, those mock-up specimens being fabricated in Portland, Oregon as part of Supreme Group. You can see here that the fabricator and erector put in some voluntary supplemental latticing, some small angle iron to provide and ensure that they had the rigidity that they wanted for these panels. They didn't want to totally trust that the cross ties themselves would provide the rigidity that was needed, and they were really concerned that they didn't want any of these to rack. You can see here a coordinated and pre-installed MEP opening, kind of replicating all the different parts and pieces. This is the panels being lifted off the truck, and you can start to see these things swinging into place. And the element was off the hook in a matter of minutes. Obviously, they're working on the ground and not up in the air, but nevertheless, it showed how fast, when things are aligned properly, how fast things could be off the hook. Here is the picture, just the side view of that weld, where you've got your full depth PJP with your reinforcing fillet. Soon after, we started to receive shop drawings for the actual building, which you can kind of see here. Again, lots of different panels in this 3-cell core, pre-drilled holes for all of the diaphragm connectivity, pre-installed MEP, pre-installed port access for pumping, pre-installed shear tabs. Essentially, everything's ready to go. You just lift it and put it into place and start hanging steel off of it. This is what an isometric view of one of the panels. Again, you can see the latticing and you can see the cross ties, and all of these little buttons kind of sticking out is that 3/4 inch extension with the fillet weld around it for that particular cross tie configuration. Here's a picture of a coupling beam section or an H panel, and you can imagine if you stack these on top of each other, with this being a typical splice at waist level, 4 foot something above floor line. This is your floor line here, and this is your typical splice elevation like you'd have on the rest of your steel framing. Here's a panel just showing configuration of an opening through it. And this is what the shop looked like. A lot of laydown area, and you got to have a lot of space to be able to fabricate these panels. But essentially it was an assembly line where plate would come in on one side and fabricated panels would come out the other side. Talking a little bit about this plate, one thing of note is that given the floor-to-floor heights in the building being around 13'9", domestically in the United States, the widest plate that you can generally get rolled is about 10 feet. So below grade, where our floor-to-floor heights in the parking were 10 feet or less, all of the plate was ordered domestically. As part of this process to get wider plate, there's only 2 places in the world that we're aware of, Dillinger and POSCO in Korea. They ended up ordering these plates 14 feet wide out of Korea so that they could eliminate the need to do a shop splice. Those plates are put on a burn table and cut out to specifications, and then the elements are moved down the assembly line and then slowly taking shape in terms of the prefabricated panels. You can see a few pictures here of what that operation looks like. Here's a panel on its side. And then this is what it looked like when we got outside, getting ready for staging, shipping to the job site, and to be erected. Generally speaking, many of these panels were lifted off the truck, nearly straight into position and put into the core. Every once in a while, they'd have to lay them down in a laydown area, but generally speaking, the timing was such that they were able to pick these up and essentially put them in place in the building and be off the hook in a matter of minutes. This is a picture happens to be from our office. We reside in the building next door, so this is very convenient for us to do site observation. We could literally just look out the window. But these were the first fabricated pieces coming to the site when they got to the bottom of the hole, which was 7 stories deep. Again, just a couple pictures of those panels being lifted into the hole off the truck. And this is a picture of those first lift of steel. So the goal here in coordinating with the contractor, the general, and the erector and the fabricator was really to ensure that the core itself ended up in the right position. And in that case, they made sure and they first erected this core, the first lift of core, up in the air on these stanchions. And then they built the rebar for the mat foundation around it. The stanchion was able to deliver the full capacity of the core down into the mat foundation, and then eventually the concrete was infilled around it to create the mat foundation. This is October 1st, 2018. On October 15th, 2018, the steel erector showed up and started going vertical with steel. And pretty soon here, I'm just going to kind of slide through quite a few slides to just kind of show the sequence of construction here. And what you can see here, again, the discussion of the core being built where the corner columns were erected first, plumbed and welded out, and then the panels would fly in. And then you can quickly see this building going up vertical. This is the outrigger columns. They were constructed in a similar manner, cross ties and concrete filled boxes, again, composite sections for strength and stiffness. This is showing how those corner columns were plumbed and guyed off to ensure there's verticality. And then this is looking down at the building again from our office as it's coming up. And this is from the street. And then here, I'm going to zoom in here. This kind of shows a really good, you can see here the ports where the concrete placement was being provided. You can see the erection of the steel being done on a tier-by-tier basis where the floor framing is coming into the core at the same time. Generally speaking, you had one level of erection ongoing for the core. You had one level of the core being welded. You had, one tier being welded, 2 levels. You had one tier of the core being filled with concrete, and then you had one tier of active concreting of the deck. So the full concreting of the deck trailed by about 8 floors from the active erection deck. Here you can see these parts and pieces coming together. You can see the horizontal weld and the vertical weld and the vertical weld and the horizontal weld as these sort of erector set pieces are fabricated together or put together. BRB connections at the outrigger levels were greatly simplified because we were able to just integrate the gussets directly into the steel shapes. No sort of embeds that need to be coordinated with rebar placement. Again, we were able to just have all of this prefabricated, all these very big connections prefabricated in the shop. Here's a connection shown to how it connects to the core. And then 10 months later, on August 15th, the topping out party, the last piece of steel went into the building. So it really did hit that 10-month mark. And I'm going to you can see what it looks like. This is about on that same time of that topping out party. You can see the Christmas tree there. But the building is a tall building, about 60 stories above grade, 7 stories below, so about 67 stories in all, built in about 10 months from the bottom to the top. And I'm going to hit play on a video here, and you can just see from the bottom of the hole up to the top here, the excavation that went. There's a whole nother webinar probably to talk about this shoring system. You can see this building that we resided in was pretty precariously being held up there. But the thing of note here is just to see how the erection was ongoing and really done in that sequence where the core and the steel floor framing was going concurrently. There's a bit of a slowdown here around the outrigger level. That area was a pretty big area to put all those BRBs in. And then once we got to the single cell core, you can see how fast those 20 upper floors went in the timeline here. So Nate, I think it'd be good to maybe go to our quick assessment poll really quickly here, and then we'll go back and talk about some of the ongoing research initiatives.
All right, Brian, sounds good. So we're going to go ahead and ask an assessment question of the audience. We'll be going to a polling module here. And the audience can participate by selecting the answer that they think is correct on their computer screens. So the question is as follows. What was the primary reason that SpeedCore was utilized for Rainier Square? Is that A, to avoid rebar congestion, B, to minimize wall thickness, C, to reduce construction schedule, or is that D, to increase wall strength? Again, what was the primary reason that SpeedCore was utilized for Rainier Square?
I think they have it.
Yes. The answers are coming in fast here, Brian, so I'm going to go ahead and close the poll. And it looks like nearly unanimously the audience thinks that that answer is C. So do you think they got it right?
I believe they got it right, yes. So the answer there really for this particular project, the goal was to reduce construction schedule and achieve the ancillary savings that came with that, the cost schedule savings, the reduced financing costs, the faster to market. Avoiding rebar congestion was also achieved. Wall thickness actually for this project wasn't achieved because of the fact that we were such a tall building, we needed still thick walls. Increased wall strength, that actually was also something, but in terms of the primary reason, it was to reduce construction schedule.
All right, Brian, thank you, and we'll just have you take it home now.
Okay, thank you, Nate. So that was kind of a summary of and case study of Rainier Square, why and how and where it kind of came from, and how it was utilized to really achieve the goal of the mantra of SpeedCore, really to achieve a much faster construction sequence than a traditional concrete core would be done. I want to talk briefly here to summarize some ongoing research initiatives. Obviously, I talked about a lot of the things in terms of optimization that, given that Rainier Square was the first to do it in such a high seismic region at such great height, we took a lot of conservative assumptions that everybody could agree to. A lot of those things were based on some of the earlier research that was done by the research that both AISC and PANCAL were part of in terms of supporting. There was a design procedure for dual plate composite shear walls, which was 2006 to 2010. But based on kind of Rainier Square and the need to help optimize and provide more tests to validate and provide better design guidance to not just MKA but everybody, there's 3 new research initiatives that are ongoing. There's the seismic and wind behavior and design of coupled composite plate shear walls for steel buildings. That started in 2016, is still ongoing. There's the R factors for concrete fill coupled composite plate shear walls, which has recently concluded. and there's performance-based structural fire engineering in buildings with concrete-filled composite plate shear walls. These research initiatives are all being supported by ASC and are ongoing, and they're providing very interesting and meaningful results for kind of the next generation of this building or this type of structure. Just talking about the test, again, I showed that picture earlier. There was additional testings on planar wall sections with different cross-tie and shear stud arrangements. Those tests were kind of done in the lab at Purdue and showed good strength and stiffness and ductility backbone curves. The R factor for coupled composite plate shear walls research program really had to do with taking that planar wall research and extrapolating it to coupled walls. And this research, interestingly enough, has substantiated an R of 8 and has already passed the NEHRP PUC and is going to be going to ASCE 7 for potential incorporation in ASCE 722. So the primary research outcomes of these different research initiatives that are still ongoing is that the ASC recommended plastic stress distribution and fiber analysis methods can conservatively estimate the flexural capacity of the wall specimens. The flexural stiffness of the wall specimens in the elastic range can be estimated accurately using EI effective equations already from AISC 360 for filled composite members. There's going to be some proposed provisions for ASC 341 that include updates to sections H7 and a new section to discuss the coupled composite plate shear wall section details. There was a FEMA P695 study that has confirmed that R of 8 is appropriate for these coupled systems. And again, the hope is that once it's passed, it has passed the PUC from NEHRP. It will go to ASC 7 for potential balloting and incorporation in 722, Chapter 14 provisions. And then there's hopeful fire resistance recommendations ongoing, whether or not fireproofing is even required for a building like this. I guess I didn't say it when we were talking about Rainier Square, but one item of note is all of that steel that you saw in that was fireproofed in a traditional cementitious fire protection method. Just a quick slide here as we start to take some questions to put up here. There's more information that you can find on the research that's been done through the Pankow Foundation there. There's also a couple links here that we've added from AISC in terms of SpeedCore and how it might be designed. There is in the works some design guides that AISC is looking to create to help get more information out in the market. But all of this is still ongoing, and it's happening very fast, and the time is great now to really start looking at this and advancing this and further optimizing this Rainier Square case study that I presented today. So with that, Nate, I think we should open the floor to some questions.
All right, Brian, thank you very much. We do have quite a few questions here from the audience, so we'll see how many we can get to. I'm going to start by going back to slide, if it will respond, slide 18. And the question here is this. In terms of the analysis of this building, what does it imply, this type of shear wall in the modeling? Did you model the shear wall as concrete or somehow a composite section? Did you run nonlinear analysis taking into account the composite material?
Mm-hmm. So from an elastic design perspective, we started the building as a concrete building, as we talked about. When we went in the elastic model to convert it to a composite plate shear wall, we went to what I would call a transformed section. We essentially just put in the strength and stiffness of a transformed section of elastic plates with some effective cracked concrete modifier. There is some recommendations about those in AISC 341 in terms of effective stiffness of a composite section. From a nonlinear perspective, yes, we did do nonlinear modeling, and we used a fiber-based approach. So we modeled the fiber hinges of the steel and concrete working together in a composite action and evaluated the building performance under nonlinear procedures. So we did both a fiber model nonlinear, and then in elastic world we did a transform section. What was interesting really in the elastic world is we weren't able to really thin up the wall too much on Rainier Square because the governing demands on this building from an overturning perspective are wind. Wind is controlling the overturning moment by almost a factor of 3 or 4 relative to seismic. So we still needed the same strength and stiffness, so we still ended up with quite large wall elements at the base of the building.
All right, Brian, keeping it here, it's a question about the rest of the frames in the building, if there was anything special about them. Did you utilize SMFs or IMFs on this building?
No, we did a performance-based seismic design approach where this is an unidentified structural system. There is no backup dual system or moment frame system in conjunction with this. So this is a composite plate shear wall core with supplemental outrigger bracing, buckling restraint braces as the lateral system.
Right. There's a few questions about concrete consolidation considering the openings in this wall. Were there any special considerations in how the concrete was placed around these openings, both for in the link beams themselves and in the panels around the openings?
Yes. So what's not shown here is we might have seen it in some pictures later, but in all of the interior plates where they would create what I would call a vertical baffle, we analyzed and provided the ability for the fabricator to put in flow holes. So essentially making a little bit of Swiss cheese out of those steel plates. So anywhere we had a vertical plate, there were flow holes added within the assembly. At coupling beam elements, there were vent holes. Those allowed air to escape from those sections, and once the concrete fully came out of those and bled out, kind of like bleeding air out of brakes or something, they would be able to gate those off. Additionally, they had telltale holes or other air relief holes so that they could tell where the concrete was. So in strategic locations, there was always flow holes on interior plates and vent holes to ensure that all the air was getting out of potentially areas where air could get trapped.
Right. Go to slide 26. A couple questions about this detail. So was there any consideration by your project team of using shear studs instead of using all cross ties? And a couple of people asked, do the cross ties develop the steel plates similar to shear studs to form the composite action?
Yeah, so I'll start with the second part of that question. Yes, so a cross tie does dual purpose. It acts as like a shear stud in the concreted section to act like a composite element or ability to deliver composite action just like a shear stud would. A shear stud would not provide any stability during erection or stability during the unconcreted condition. So again, very conservatively, we took the approach that we would provide cross ties at all of these locations at 12 inches on center so that they could do all those purposes. Every one of these cross ties provided composite action in the concreted section and provided stability in the unconcreted section and provided stability of the plate during placement. That said, the research, some of the highlighted research I showed there, showed that a combination of cross ties and shear studs provided the same performance, or generally the same performance, as a wall that had all cross ties. So if you were able to intermix and space out or alternate space cross ties and studs and still satisfy the unconcreted section and the handling stiffness requirements, you could certainly use a combination of cross ties and studs.
All right. Looking at this detail near the corner of the shear wall core, there's a question, do you know what site welding method was used and how did that work with regards to the tolerance between the adjacent modules? That is, any gaps between abutting plates and the variability of the gap over the height or the width of a module?
Yes. So these were not automatic weld. These were hand welded. They attempted in the mock-up to do some automated welding procedures. And what they found was that, just as the question sort of alludes to, the fit up, you never have a root gap that is generally maintained along the length of these. If you look here at these two locations, there was only a 1/4 inch root gap designed in the panel. So from a tolerance perspective, these two corner panels are, let's say, 40 feet apart. This panel's 35 feet long. You only had a 1/4 inch gap on each side of tolerance. So these panels had to be, or these corner columns had to be very plumb. But that root gap could be 0 on one side and 1/4 on the other, or it could, at the horizontal, be 0 at one side and vary to a 1/4, just because of tolerance. What they found was that automated welding that they tried would not be able to adjust to that variability. And so they ended up doing human hand welding. It's not stick welding, but just kind of, I don't know the right terminology, but they ended up hand welding and field welding all of the without any sort of automated process.
Some of the photos appear to show some lateral distortion in the panels between floors prior to the concrete being placed. What was the out of plumb measurement that was encountered during construction?
Very little. I don't know a number, but what we can say is that this picture we're looking at here, the intent of this picture was to push this panel to the limits and actually force buckling. There's a paper and some research that was done by Purdue that they've now published, which has now prescribed simple methods to calculate the critical buckling stress for a composite plate shear wall panel. And so as long as you're outside of that buckling stress, what you find is that we didn't see much distortion at all. In fact, we used 1/2 inch plate pretty much throughout. They placed concrete in a floor-by-floor manner, so only a hydrostatic head of, let's say, 14 feet nominally. What I can say is when you look down a wall panel before placement and after placement, you can't see, with that 12-inch spacing of cross ties, you can't see visually any distortion. As you start to maybe push that to 18 inches on center and things of that nature, maybe you might start to see some distortion. But one of the things we're looking at on future projects is to space those cross ties out and potentially be pumping more, depending on the size of the core. Maybe we're going to pump, 2 heights at a time, two lifts at a time. That could start to control how much bowing you might get during concrete placement. But again, we would limit it to a pretty small number, maybe a 1/16 of an inch or some sort of B over ratio. But again, in Rainier Square's case, there was no observed distortion of any of the panels.
So we had a question of how did you prepare, or how did you prep the construction joint between wall lifts for the concrete placement? I believe that's a preparation of the concrete interface itself.
Yep. There was no preparation. It was a self-consolidating concrete mix. There was no sort of roughening requirement. Given the composite action with all the different cross ties, we weren't concerned with cold joints. So in general, there was no special requirements for any sort of concrete preparation for different lifts.
Did this project use BIM with model sharing between the engineer of record, general contractor, and fabricator? Could you describe how that went for this project?
For this particular project, the architect and engineer, we did use BIM in terms of reference models. To be honest, our BIM model is very rudimentary compared to what you're seeing here on screen, which is probably coming from Tekla. We were certainly sharing information with the fabricator, but really we didn't dictate where splices needed to occur. That was a fabricator choice based on many considerations: shipping restrictions, erection sequencing, pick weights. So all of those came into consideration, and in the end, the contractor, one of the first things they did was take our wall elevations and decide where they wanted to put all the splices. So what you see here really was more working in the world of the contractor's model which a lot of that value really came in. There's certainly things that we don't see when we put it in our BIM model. So I'd say that process of what their modeling and their detailing model did really kind of flushed out a lot of the details.
All right. Well, thank you very much, Brian. Unfortunately, we're a bit out of time here and can't get to any more live questions. Thanks again to Brian Morgan for presenting today's webinar, and thank you all for joining us. Have a great rest of your Friday, and happy Steel Day.